Yeah, good morning. Can you hear me?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah, okay. So, what was the last topic? Which topic did you discuss? Yeah, what was our last discussion here? Anyone, please?
Sir, last topic was on Lorentz force equations, sir. We completed that and we wrote an exam on it.
Okay, so also I think we are done with, simple Fleming's left hand rule, right?
No, sir. Fleming's left hand rule is not
A
completed.
force experienced by the current carrying conductor using Fleming's left hand rule.
No, sir. You told that you will tell in the next class about the
Okay,
Fleming.
okay. Anyway, so I did not discuss about force between two parallel current carrying wires, right?
Yes, sir. You did not discuss.
Okay, fine.
Yes, sir. Thank you.
So, okay. So I think you all are seeing blackboard. So okay, first we'll go for this force between. What I mean to say about Fleming's left-hand rule is it's quite simple. That is, I mean, one second. Let me take some water. So okay. So just uh, so direction of say magnetic force, direction of magnetic force on a current carrying conductor. That means we can use now Fleming's left hand rule on a current carrying. Yeah. So we know from the Lorentz force, the magnetic force, we can take it like this: I, length of the conductor in terms of vector we have, and B, magnetic induction vector we have. So we can use either you can use right hand thumb rule, or you can use right hand palm rule just to find direction of magnetic force, or I can use let me write like this: Fleming's left hand rule. So Fleming's. Okay. So for example, we have some. Uh, Take another space, or I'll put it down here. No problem. Say for example, this is my direction of magnetic induction. I have a uniform magnetic field. Say I have B. So now uh, I take some current carrying conductor. Take some current carrying conductor. Okay, so this is this, and say uh, the length is L. and this is carrying some current I like this. Okay. Now say this current carrying conductor, this is Mn. I have this segment Mn here. So current is in upward direction. Okay. Now just take your left hand. You know what you do? You take your index finger and middle fingers. Okay. Now you can take your left hand. So let me take my. It's getting stuck here. So I'm just trying to draw this. You adjust. Okay. So this is your finger. Okay. How many fingers this guy is having? Okay. And this is your say. I mean, this middle finger I have. Along this middle finger, you have direction of current. Along this index finger, this guy, you have a direction of B along this. And now you're seeing this one, the thumb is into the board, okay? The thumb is into the board like this, and this is what the magnetic force. That's it, okay? So you can take this way, middle finger. So middle finger is I. Whenever you have I, you can assume you have a positive charge flow. Otherwise, I is C. I is in this direction means electrons must go in this direction. It's conventional current. And now the thumb will be your direction of force. So this is your magnetic force. That's it. Okay. And you can take your index finger. Your index finger will be direction of B. All right. And similarly, also I can use right hand palm rule. How? Simple right hand palm rule. Along this direction of uh, current, you put your thumb. Okay. The palm fingers, whatever fingers I have, this is towards B. This guy is towards B, and this is I. And where is your face of the palm? The face of the palm is into the board. So this is your force. So this is your force, yeah, or magnetic force. I can say Fm. Yeah. Are we clear so far?
Yes, sir.
Yeah. So Fleming's left-hand rule is no big deal for you to uh, understand. There is nothing. Either I can use left. See, this is must be Fleming's left hand. I mean, not your right hand. You must take your left hand and do this. Otherwise, if you're really comfortable with right hand palm rule, you go ahead with that. But for me, I always I always believe right hand palm rule will help us in many situations. It's not supporting. So this is winter. State to one. Now I take force between two parallel. Let me take force between two parallel current carrying conductors. Now, this is very important question for examination also. For example, say I have one long wire. Okay, let me take a long wire like this. I have one long wire, and other is a finite length short wire. Okay, think like this. You have two wires. So one is a long wire, and other is a short wire. And name this short wire as something like Mn. This long wire is carrying some current I1. So this fellow is also carrying some current, say I2. Okay, and Let's take the length of this short wire Mn is of length L. Now anyone in the class, see, okay, the distance, okay, at a distance of say R units, at a distance of R units from the long wire, we have a short wire Mn. Anyone in this class, how would you see the force? Whether you have force of attraction or force of repulsion between these two current carrying conductors. So what do you see now? So what do you feel now for whether these two current carrying conductors will tend to attract or they repel? Attract means they need not come in contact. The thing is that two wires need not come in contact. Attract means they come closer to, okay? Or repulsive means, they will not go somewhere, some several meters away. So they repel to some extent, anyways, from some point of reference. Okay, now, now what do you think? So two current carrying wires we have, one is long and one is short. Okay, so what do you think whether you have force of attraction between these two or force of repulsion between these two current carrying wires? Anyone? Hmm?
Attraction, sir.
Very good. So yeah, we'll make a note of it later. Whenever two current carrying wires, whenever current is in same direction in two wires, so that they tend to attract. Okay, if they're anti-parallel, now exactly they're parallel. Now, if I1 is coming down and I2 is going up, then definitely there will be repulsion between these two current carrying wires. That's a very great experiment. And this is telling us something interesting like this. You see, let's start doing this. So let me write magnetic induction. So magnetic induction, say due to this guy, due to I1, at the location, of conductor, say Mn or wire, whatever. Okay. Yes, anyone? So what you get now? What is B1 now? You
mu
just
naught I by 2 pi r.
By R.
very
Not
good.
I.
So as I have a long wire, so due to long wire at a distance of R units, at any point a distance of R units, I have a very correct mu naught I1 by it is 2 pi R. So how do you think that the direction will be? See, put your thumb along this I1. You put your thumb along this I1 and stretch your right hand palm, okay? And otherwise you curl it. You curl your right hand fingers, four fingers, you would see the magnetic induction like this. This is B1, okay? So B1 is into, see, due to I1, magnetic induction B1 at location of Mn is this one. All right. So now you tell me, how is the force due to this B1? How is the force acting on this Mn? How is the force acting on them, and how is the force means in which direction? Into the board, left, right, or out of the board? Hmm? Anyone?
Left.
Very good. The force will act left. How? For example, you see,
Right.
let me take, very good. You can use your again right hand palm rule, okay? So this is my force. So this is my force here, okay? So how? It is quite simple, you see. You stretch over, you stretch over, okay? So this guy is your thumb and your palm is this, okay? Your palm is this. Now you see along this thumb, what do you have now? Along thumb you have, what is this current, right? This is I2. Now how do you have B1? B1 is into the board, right? So this B1, those four fingers you have to show into the board. Now the normal to this palm is what now? This is the force. Yes or not?
Yes, sir.
Yeah, and that's what you have. So the force you have like this. Similarly, now what do? Similarly, you can do this. According to Newton's third law, definitely what we can see is we can do this. Newton's third law says that, yeah, every action has equal and opposite reaction. Okay. Otherwise, what do? You put your right hand. Now see, you find magnetic induction B2 due to this current carrying wire Mn. Okay. You take your right hand thumb. You take your right hand. I'm right hand. Right hand. You put your thumb along this current I2, and now you wrap your fingers all around. Then what do you see? Due to this, so I can see this one. So due to Mn, due to Mn, at this point I can see B2 is coming out. Yes or not? Due to Mn, right? Yes or not?
Yes, sir.
Yeah.
Yes, sir.
So that
Yes,
is
sir.
true. So therefore, now again you put your you take your right hand palm, you stretch your four fingers. Okay, you just take your right hand palm, and you twist it. Okay, twist means you put your four fingers toward you. This four fingers towards you. That is B2, and I1 the thumb. Okay, I1 is along your thumb. Now the face of the palm, the normal to the face of the palm is towards the wire Mn. So this is what you have. This is of course again Newton's third law also says this. This also behaves. This is also taking this law into consideration anyways. So you have now you can see two forces they are trying to show in one opposite to each other. Now and what about the magnitude of force? Do you think you have same magnitude again? So this green vector and this vector are the same or the different?
Different.
Different.
Okay. You go home and think whether they are same and different. If I tell you yes they are same, then you comment on this. If they see, okay, let me say they are same. Just comment on this, take it as task and just tell me. And if you have the answer they are not same, then again come with the answer. Just take it as a small assignment, okay? So anyways, what I have is magnetic force, magnetic force on wire AB. Magnetic force on wire AB is what now? Can I say like this? What is this? Anyone? What is magnetic force on wire AB? I want to find this force, this magnetic force on wire AB. So I know Bill, right? So I have magnetic induction due to this current carrying wire I1. Okay, B1, I have I2 multiplied by L, right? So now what is B1 here? Now my B1 is this fellow. So just plug in here, mu naught I1 by 2 pi R. Okay, and this is I have I2 L. Otherwise, simply I can say this is magnetic force between two wires. I can say simply magnetic force between two wires. See, I can have two comments. One comment is I can say magnetic force on wire AB. I took AB here. I took Mn, right? Magnetic force on wire Mn is B1 I2L. Or simply I can say this statement as magnetic force between these two wires is again the same B1 I2L. And B1 I know, I2L, just plug in here, that's it. So now what you have is that they tend to what now attract. So this is what attract. Now you do one thing, you go home and test this. What you do now, please test these things. When something is given to you, you please test and come out with the results. That's what you must do. Okay, say one conductor is something like this, carrying current say I1, and another fellow is carrying current I2. Okay, now see the current is, say this is Mn. This also can take a finite length wire, not a problem. Let me take this is okay. I don't take AB. Let me take some PQ. Okay, So in this case, I1 is up, in this case, I2 is down like this. So you find, say, the distance of separation is R. Okay. Now find the force formula for this, and also its vector. So in the form of direction. Okay. Now what do you think? You think magnetic force is like this, right? Yes or not?
Yes,
Yes,
sir.
sir.
Force
sir.
must be like this. So whenever you have two current carrying conductors, and if the currents are running like anti-parallel, one is up, other is down like this, they tend to repel. So this is a straightforward stuff. 1 second here, let me take water, my throat is not supporting. Starting out like this, how can I teach MATLAB session in the evening? Some water will definitely help us. God is so great. He gave us everything. Uh, You know what? If you don't take at least 10 glasses of water a day, if not 10, 6 glasses of water a day, your kidney will become dangerous. Okay, kidney is very important, and this is not required to say. Save this. Okay. If I ask you a question like this, so you know how to find a magnetic force when I put a conductor exactly normal up perpendicular to the magnetic field or at some angle to the magnetic field, you know how to find all those things. But if I give this one magnetic force, I don't think this is not in your syllabus, but I'm just giving you, just go home and work out on this. Say magnetic force on a random shape or a random shaped current carrying conductor. Take some random shape. For example, you see you have some magnetic induction. Direction of magnetic induction is into the board. So P is into the board. Now, so in this scenario, what I do, let me take some path. Okay, let me take some a current carrying wire like this. Okay, and this point, let me name it as M, and let me make it to give a good feel. Let me make like this. Okay, I have some current carrying wire. The wire is somewhat random in shape. Let me take two ends, M and N. So this fellow is carrying some current, say I. This fellow is carrying some current I. Okay, now it is having some length. Now how do I take the length? The length in this case I'll take it as like a displacement quantity, displacement say from M to N. And for that, what I do, I just take like this. Okay. Now, can anyone find this magnetic force on a random shaped current carrying conductor? A magnetic induction is into the board. Anyone? Yes. Yeah, just think for just 1 minute.
Sir, can you do it by integrating?
You try, no, how do you have this? Okay, you can do integration, whatever you want to do. I can give you some hint, okay? Now, for example, you can take some length of this segment. Now, for example, let me take this. Okay, let me take this guy. Anywhere I can take, right? Let me take DL here. So let me take my DL. So this is my ideal. So say I have a DL vector like this. Now you can, I drew somewhat a vertical one. I could have done something, could have tilted this. This is say x-axis, okay? Now you draw its perpendicular. This is like, you can make this one as, I'm just giving you some idea. This you can make something like y-axis. Now, so you have, okay, let me make it neat. This is like your x-axis. A y-axis, you have a current carrying, a random shaped current carrying conductor. Then how do you do? Yeah, please do one thing. You please go home and try working on this. Yeah, if you try working on this, you will get something interesting. And whatever you said, integration will definitely work out here. Okay, that's great. You go home and try it. Integration will definitely work out. Okay, so just give a try. What is there? What is wrong in that? But this fellow is not in your syllabus. Okay, if you want, I can teach this for you. Otherwise, not a problem. So today my throat is completely not supporting. Okay, just please go home and try this. Let me take one simple question for you. Okay, please write this question. Mm, a rod AB of mass m is placed. A rod AB of mass m is placed on two smooth rails. Is placed on two smooth rails, say P and Q. Okay, in a uniform magnetic induction, say B, in a uniform magnetic induction B. Okay, you can see like this as shown in figure. Okay, and right, the rails are connected. The rails are connected to a constant current source. The rails are connected to a constant current source, say of current of current I. Is my voice low or perfectly audible?
Audible, sir.
Audible, sir.
Audible, sir.
Okay. So fine. So find. Okay, I'm just making a basic question. The speed, mass kind of things means we often don't require to observe, but this is interesting to observe. Okay, find the speed attained. Find the speed attained by rod. What did I take? Rod AB. Okay. Find the speed attained by rod AB. Let's not take AB. Let's take some. Let's give some name. Mn, because B already we are using for magnetic induction. Find the speed attained by a rod Mn when it leaves off the other end of the rail. The other end of rails. Okay. So this is a very simple, very simple question is this. Say you have two rails like this. I have a rail 1 and I have one more rail. Okay, so I have two rails like this, and let me take a current source. We take a current source. This is a voltage source, right? So let me take a current source I, and let me connect this fellow to this. Okay, if I ask you, will this radiate here? Say these two, this green two wires you have. Sorry, will there be current in this loop now? Anyone? You are doing circuit theory, right?
Yes, sir.
You all are doing circuit theory. Can I ask you one question? For example, you have some source here. You have some source, and I have wires like this, and there is no. It is open over here. If I ask you, will there be current in this or not?
No, sir.
No, sir.
How many of you say okay? Can you raise your hands? How many of you say no? Raise your hands just to say what is there. I can see in participants window. Just raise hand. How many of you say no? What about remaining? Why are they thinking so much for this? It is so difficult question here. It's a minimum common sense question, I think. Kishore Yadav, just mute yourself. Okay. What about remaining? Huh? Gogirani Pujita, what about you? Okay, then remaining are okay. Remaining they are not saying. Remaining they okay. Remaining say they remaining. Remaining are saying that there is current, right? Yes or not? I want some response. What about remaining? I'm seeing few hands up. What about remaining hands? So, Alekia, could you tell me why there is current in that? How do you say there is current in that? Alekia, roll number 38. Roll number 38. Please unmute yourself. Unmute yourself and turn on your video and just give me the answer. Alekia, roll number 38. Roll number 38, is she there? Okay, so say roll number 38 is absent. So let me take some absentee list. Otherwise, I forget these things. Okay, that's what I'm taking. And Someone else. Bal Gangadhar. Is he there? Roll number 13. Roll number 13, Bal Gangadhar. Are you there?
Sir,
You're there, right?
sir,
I could not see you. Where are you, man?
sir,
Yes, who is calling me?
sir, 13, sir.
13. 13, where are you? Just turn on your video.
Sir. Sir, on చేసే sir.
Someone turn on. Ah, just tell me whether there will be current in that loop or not. In this loop, whether there exists current or not. Roll number 12, Stravia. Roll number 12, Stravia, please turn on your video, mute, unmute yourself, and just tell me. I don't know anyone in your section really. I think I'm your AMC, but I should see. Yes, roll number 12. Okay, so number 12 is absent. Alekia is absent. 12 is absent. And V. Mohan Reddy, 34. 34. Okay. I don't know what are they doing. 34 is absent. And whom do I call? Shashank Reddy, 50. Shashank Reddy, absent. Roll number 40. Roll number. Okay. Roll number 16. Ram. Okay. So you're thinking that it is Zoom will take automatic attendance, right? But of course, we are also maintaining attendance separately. Okay, so things will update here also. Don't worry. So, roll number 52.
Yes, sir.
Yeah, could you tell me whether there is current or not in this loop?
Yes, sir.
Well, I have some source here.
Yes, sir.
I have current carrying, I have conducting wires like this. So will there be current now? Will there be current or not?
No, sir.
Why no?
Sir, because it is an open circuit.
So in open circuit, current cannot exist, right?
Yes, sir.
So that's what you are learning in circuit theory. But when you come to field theory, yeah, according to circuit theory, of course. Okay, that means if there is no current in this, you're saying that there is no current in this, okay, because it's just open like this. Then think of this one. See, you must keep your time busy in all these activities, learning things. For example, I have some source. Okay, I have some. Let me take some source. Okay. What do you have here now? Capacitor. Okay.
Capacitor.
This is a voltage source. Do you have current now? Do you have current now?
Yes, sir. Yes, sir.
See, this is a conductor. This is also a conductor. So free electrons are there. But what is there in between these two plates?
Sir, capacitor stores energy.
But,
It stores current in the form of electric field. So
it stores current in the form of no. Current cannot be stored in the form of electric field.
sorry,
First
sir.
of all,
Energy in the form.
what I'm asking you is that what is there between these two plates?
Sir, dielectric.
So it's not a conducting medium. So how can you say you have current in this? Don't you think that this is like open circuit? If dielectric is there like this, don't you
Yes,
think it's
sir.
open circuit? Yeah.
Yes, sir.
If you extend this circuit is something like this only. Yeah, of course, something like this. That means here you said there is current, but here you're saying there is no current. How? That's what field theory, okay? So field theory says there is
Yes.
current, circuit theory says there is no current. So anyways, circuit theory is Chotu. That means circuit theory is subset of field theory. Field theory is like mother, circuit theory is like a child. Yeah? Circuit theory is just approximation, but field theory is the reality. You have Ohm's law, something like what you say Ohm's law? You say V is equal to Ri.
Yes, sir.
Only is it Ohm's law or anything else? Whenever it is Ohm's law, we always say V is equal to Ri. This is also Ohm's law, right?
Yes, sir.
And also I have 1 by C IDT is also Ohm law. So I have various forms of Ohm's law. I have some 9 ways of representing Ohm's law. But in field theory, Ohm's law is J is equal to sigma E. This is Ohm's law in field theory. From this only, all the stuff has been derived, whatever. So you are learning mother subject, okay? So when you are learning mother subject, you should not say there is no current. There is current, of course, okay? But that you can experience only with the help of modified Ampere's law. So Ampere's law failed in this reason only. Like uh, like you just cornered, Ampere also just got cornered that time. So he could not understand what is that. Then Maxwell came forward and he solved the problem, and he just added, see, we have one of the Maxwell's equations, right? That is curl of H. What I know, what we proved in this one, right? Curl of H is equal to J, we proved in Ampere's law. So Maxwell just added this. And this is one of the equations, Maxwell's equations we have, okay? So with this, we can identify, yes, there is a current called as displacement current. I think you have learned that concept already, displacement current, maybe in your +2 sometime, some maybe 1 or 2 years ago. Okay, so whatever, this is simple stuff. There is no big deal. Now, let me put my conductor on those two rails, okay? Let me put my conductor on those two. So I have my rod. Okay, you can put your hands down. So let me take my rod. Let me take my rod like this. Yes, this is my rod. So you have two rails, P and Q, and you have this rod. This is your rod, say M, N. You have current like this, and magnetic induction is given like this. Okay, in a uniform magnetic field, this setup is there. So I'm just showing here. The cross indicates magnetic induction is into the board. Anyone who can solve this question? Who can solve this question?
Sir, it will stay in one place only, sir.
Oh, means it will stay in one place only. That means it will not leave off the rails, right?
Yes,
You
sir.
mean to say that? Why?
Yes, sir.
Definitely, because see, I don't know how you're saying that. You have magnetic induction into the board, and you
Bike, sir,
have
palm loop.
no, okay. You have a current carrying, I mean, you have a conductor, a rod, a conducting rod. We have like this Mn on the rails. Now, you see, what I can say is that this current I is going all the way like this. When current I is going all the way like this, so definitely it has this tendency, see? So it's going all the way. I can take like this I, and again like this I. This is my I. I have a conducting rod Mn, and I can assume this model now. Now this current I, whatever current is flowing through this wire, say or rod, whatever it is, through that Mn. Now what do you do? Now if you apply, now how this rod will experience force? You take your right hand palm, you put your thumb like this. You're saying no, how? You put your thumb, is very difficult to draw man every time. Let me show my hand. Okay, so this is your hand. Okay, let me show my hand something like this. Your thumb is this way. Your hand is this. Okay, so magnetic induction is into the board, and your thumb is current. Now, how is the palm here? The face of the palm is like this. So the normal you can draw this way. Yes or not? Yeah. Now
Yes.
how this
Yes,
fellow will experience force? You stretch your right hand palm, okay? Along this eye, you put your thumb. So thumb is down and four fingers are into the board. And therefore the force experienced on this current carrying wire Mn is like this. And you could see that this Mn is moving towards right. Yeah. Now with what force he is moving now? With what force? What is the force there?
Sir,
Magnetic.
BIL.
Yeah, it's B, magnetic induction I have B. So I have current carrying I, and say the length of this rod is some L. Okay, if I take length of the rod as L, now I have this force, BIL. Okay, so I have force like this. So the force is moving towards this. If I put this is some x-axis, I can take the vector here, something like x-axis. That depends upon the axis. Now,
So we can take force as MA and then we can do it.
okay, you can take, for example, this extreme here. You can, anyways, this Mn will move along the rails PQ. You just come up this extent and think what happens. Just do it now. First put pen on the paper and do. So this is a little, I mean, I don't know. You can just take 2 more minutes. You try this. You do one thing also. Okay, let me help you out like this. You also take acceleration into picture.
Yes,
You
sir.
can,
So I got
Sir,
the answer, sir.
yeah. What is the answer?
So I got root over 2BIL by M
Hmm.
into capital L.
What is capital L there?
Just a minute, sir. No, sir. Sorry, it's 2BIL by M, sir. Root over 2BIL by M.
Root over 2b I
By M.
by m.
Yes, sir.
Sir, L.
2BIL, sir.
IL. Sir, IL.
I small l.
Yes, sir.
Okay.
Root over 2BIL by M, sir.
Great, but only this L or anything else you have? I did not give any length of rails. Did I give anything in the question length of the rails? Also, you have to take length of the rails into consideration.
Length of?
The rails. The
Okay.
rails, PQ, whatever. Okay. Okay, we are taking this one as small l. Take this one as some capital L. Okay, this is small l.
Okay,
And
sir.
this
Sir,
is
into
capital
capital
L.
also there, sir.
Yes, you must get also this one.
Okay,
Very
sir.
good. So when you are getting this, and this is your say speed of this is your speed, I can say. Okay, in a direction that becomes velocity, anyways, that becomes so. Very good. Whoever get this, that means you have some physics stuff with you. That's great. See, if you take some Sadiku textbook, this is Sadiku example. So this is unsolved questions of Sadiku. This is a very good question, but of course, very simple question anyways. There is no twist in this question. Okay, it's very simple. It is just straightforward. I took snap of this base for this absentee. Okay. So whoever didn't understood this, for them, I'm just doing that here. So I know force experienced by the rod towards right, and that is Bi small l. A small l is length of the rod Mn. Okay, sliding on the rails PQ. Now we took length of the rail, length of the rails, length of the rails we took, that is say PQ. Okay, sorry, this is say capital L, and length of the rod, length of rod is equal to, you took now smaller. Now say you initially you have your rod, I think your rod is somewhere here. Initially your rod is somewhere here. Yeah, it experienced force, it's moving like this. Now from here to here, your rod is trying to cover the journey. Now here you must see what is the final velocity attained by the rod at this point, so that it will take off. It will leave off this rails PQ with some velocity or with some speed. I can take V. Okay. So for that I know the acceleration I can take like this. So experienced is VIL by M. Okay, now the thing, when the rod is reaching from one point to other point, this point, now the final speed, I'll take speed, let me not give any direction to this. Final speed, I can say attained by the rod, attained by the rod. Now what you can take, say V square is equal to U square
V
plus
square
2AL.
minus Q square is equal to 2S.
Yeah, so I can take, this is now capital L, right? Because final velocity can be, final speed can be attained. Once we are here, just here now, just we are going to take off. That means we have to cover this distance, first of all, this capital L distance, to reach from this end of PQ to this end of this right PQ. Now, finally, what is my U now?
0, sir.
Yeah, U initially here I have, here I'll take U is equal to 0. So therefore I have V square, or V is equal to square root of 2A capital L. Okay, 2A capital L, and you plug in this A here. Very good here. If you're doing these things, means you have some good grip on your basic physics. But if you take Sadiku unsolved questions, most of the unsolved questions of Sadiku and this great book of Feynman unsolved questions, you will find most of the physics-based questions, means whatever you have learned in physics. So very soon we are going to come to engineering convention, that is we use all cross products, all these things, everything in that form. So if I ask you something this way, what is means in the application based question, maybe force between two current elements. For example, let me save this TO5. A quick reference is this. I ask you, say, force between two current elements here. So Mr. Oersted and Ampere collectively established this experiment. And Mr. Biot and Savart, they are not one. They're Mr. Biot and Mr. Savart. They are colleagues of Ampere. Yeah. For example, anyways, say you have a loop like this. I have a loop. I have some loops. Someone raised. Yeah, someone gave answer. So anyways, I have, this is positive terminal, say, so therefore current is something like this, I1. This is loop 1. Let me take some loop like this. Okay, so this is my voltage source V2. This is a voltage source V1. Say as it is source, current has to enter at negative. That means current is leaving out like this, I2. Say you have some segment, okay, let me take some small segment, current is going like this. So I have current element I2, say DL2, okay. So in this case, say, let me take this one. So I have current element I1 DL1, okay. So I have like this. Now if I ask you force between these two current elements, I1 DL1, I2 DL2, anyone? Can you find? You can use your Biot-Savart's law. Okay. So anyways, both current elements, they produce their own magnetic fields. So you can find the forces, individual forces you can find, say, the distance between these two guys, say, let me take like this. Okay, let me take this as a displacement vector. So let me take, this is a displacement vector. Now this is say loop 2, from loop 2 to loop 1, say the position vector, displacement vector I take like this, arc21. Okay, I would like to find, because of this, I would like to find df1. So see, I2 dl2 will induce magnetic fields somewhere here, all around this current carrying conductor. So therefore, if you want some induction here, okay, you take some magnetic induction here in this case. Now what happens? Now here you can see this guy, this B2 or DB2 will just come out like this, and stretch your right hand palm. Okay, you put your four fingers towards you and thumb along I1 DL1, and you could see the current. I mean, you could see the force on this. Okay, this is say DF1. This DF1 is force due to I2 DL2, and this DB2 is magnetic induction due to I2 DL2. You have this stuff. Now what do? So I can find this DF1 is I1 DL1 cross DB2. Agree? This is correct, right? So this must be, and according to Biot-Savart's law, what is DB2? What is DB2 now?
Mu naught by 4 pi
Mu naught I2
dl.
DL2 cross, okay, let me take AR21, there I have AR21 by, so what do I get here? R21 squared. So mu naught by 4 pi must take here. Okay. So now, so I just put this now. If so, what is DF1 now? So I1 DL1 cross, you have mu naught I2 dl2 cross ar21 divided by, I can put all divided by 4 pi r21 square. This is cross, not multiplication. Okay. If I want the total force or the net force on the current loop, this current loop 1, the net force F1 is equal to what? Let me take mu naught I1 I2 by 4 pi. Now this is a closed loop, right? So closed, so loop 1, and again I have closed loop. This is closed loop 2, and now you have dl1 cross dl2 cross ar21 all divided by r21 square. Is it clear? Is this clear?
Yes, sir.
Yes,
Yeah,
sir.
this is highly a vectorial representation. This is very simple. You know, this equation was established, I mean, this experiment was established by or conducted by Ampere and Oersted. Yeah, and at that time, you know, these two fellows, they are colleagues of Ampere, they're enjoying this experiment. And now we're enjoying this experiment and how they tend to attract or repel all the stuff. So that's it. So we will discuss the rest of the story in the next class. Thank you.
Thank you, sir.